Welcome to our webinar series on Unsteady CFD in ANSYS Fluent. The techniques you will learn today are applicable to any unsteady CFD problem solved in Fluent. We have complete series of CFD training and consultancy for students and professionals. Please contact us for more details. Let's start with webinar. In this slide we will discuss about the learning outcomes from this webinar. First we will learn how to set up transient case in Fluent, which includes Number 1. Fluid properties. Since we are only given the Reynolds number of 150, so we will assume and/or calculate other properties using formula for Reynolds number. Please note that Fluent does not take Reynolds number directly, so we have to put parameters in such way that gives us the required Reynolds number. Second thing which we will learn for setting up transient case is how to calculate time step, number of time steps, and how long we should run the case to get the enough data for calculating important parameters such lift coefficient, drag coefficient, Struhl number, etc. We will discuss these terms one by one if you are not familiar with them in next slides. Then we will learn how to set up monitors for drag and lift coefficients. Also we will see how to create a point in fluid domain and use surface monitor to check the convergence of transient CFD. In the second part of this webinar we will use solution data we have just gathered from CFD run, to calculate the mean drag and lift coefficient. Also we will use these data to calculate the Struhl number using fast Fourier transform, also known with its famous acronym FFT. You will also learn how to make animation for transient CFD. In our case we will use this feature to capture the vortex shedding pattern behind the circular cylinder. I will also show you how to make vector and contour plots. We will use circular cylinder at Reynolds number 150 to demonstrate how to set up transient case in Fluent and post-processing unsteady data. You will also find out drag, lift and Struhl number and compare it to given experimental data. The reason for choosing this case, as you also see in next slide, is that after Reynolds number of 200, flow becomes three-dimensional and exhibits a complex laminar turbulent behavior, which is not possible to predict correctly with RANs. You may require large eddy simulation, which is computationally very much expensive. Again, at very high Reynolds number flow becomes fully turbulent and RANs can predict flow parameters reliably. We will see this one in our next webinar. Stay tuned and visit our page to get registered next webinar. Here flow around circular cylinder is shown for different flow regimes. Our problems lies in the third flow regime from top, which is dominated by the laminar flow with vortex street in the wake of cylinder. For higher Reynolds number flow is mix of laminar and turbulent regions, which requires transitions models or large eddy simulation. Please be careful in applying transitions models. Once the flow becomes fully turbulent, we can again use Reynolds averaged Navier-Stokes equation to accurately predict the flow parameters. We will compare Struhl number and mean drag coefficient from our CFD simulation to be done in Fluent with the experimental data shown here. You might witness some discrepancy in CFD and experimental data for drag coefficient, which is normal. In literature, many researchers have also found the same discrepancy. For this case, we have chosen Reynolds number of 150, which is the upper limit of flow regime we have selected for this study. From the fluid dynamic point of view, Once you match the Reynolds number, you are able to get the same flow behavior and flow parameters as done by someone else. We can choose any value of variables in Reynolds number and still we get the same results if combination of these parameters do not alter its value. It is one of the advantage of CFD as compared to experimental methods that we do not have any limitation of size, material properties, and flow conditions. For example, we can use very high temperature in CFD, but it is not possible to do it in laboratory. Let's assume that diameter of cylinder is 1 meter, flow velocity is 1 meter per second and density is 1 kilogram per meter cube. Only parameters left is viscosity, which can be calculated as shown. Its values comes out to be 0.006667 pascal second. We will set these values in Fluent for material properties and boundary conditions. Domain extents chosen for this study are 20 diameters upstream, and 45 diameters downstream. In the positive and negative y direction, domain extent is also 20 times of diameters. This is to ensure that flow does not get reflected and produces the erroneous results. 3 meshes are created using ISM-CFD hexo in order to access the mesh independence of results. Mesh has very high quality, especially in vicinity of the circular cylinder wall, where mesh has very low aspect ratio and high orthogonal computational cells. Wake is highly resolved, as we know that for this problem, majority of drag comes from the pressure part of drag. It is also important to accurately resolve the vortex shedding behind the circular cylinder. All 3 meshes have double the nodes of previous mesh. It is achieved by increasing the mesh size in each direction by factor of 1.44. For 3-dimensional case, please use the factor of 1.25 in all 3 directions to increase the overall mesh size by factor of 2. Minimum orthogonal quality is 0.75 and maximum aspect ratio is approximately 33. For inlet, velocity inlet boundary conditions is selected. For incompressible flows, it is the most suitable boundary condition for inlets. Please put the 1 meter per second for inlet boundary conditions while working in Fluent, as will be shown in next part of webinar. For outlet, pressure outlet boundary condition is prescribed with 0 gauge pressure. Operating pressure or atmospheric is set to 101,325 Pascal, which is default setting in Fluent, so we will not change it. It implies that at outlet we have absolute pressure equal to 101,325 Pascal. As absolute pressure is sum of gauge pressure and atmospheric pressure. For top and bottom boundaries, symmetry type is assigned. It is to ensure that flow do not form boundary layer on these boundaries. You can also use wall with 0 slip. Or you can also use translate periodic boundary type for these boundaries. Only consideration you should keep in mind is that you should avoid convergence issues. Otherwise these boundaries do not play any important role in flow parameters of interest. For cylinder we will assign wall with no slip condition. Please note that no slip condition is default option for wall boundary type in Fluent. There are many methods to calculate the time step, know of time step and total number of time steps. For turbo machinery such as vertical axis wind turbine, we may use the time it takes to complete the 1 revolution around its rotational axis. For combustion we may use the time it requires to completely burn the fuel. For this particular case, We are interested in vortex shedding and DAG, which is function of vortex shedding frequency. From literature we found that the vortex shedding depends on Struhl number, and which is function of Reynolds number. For this Reynolds number experimentally found Struhl number is 0.172. Now using the formula for Struhl number, as shown here, and using values of velocity and diameter, frequency is calculated to be 0.172. Now time period needed for one vortex shedding cycle is reciprocal of frequency, which is found out to be 5.8139 seconds. Now we want to divide this time period into 20 equal intervals. If we use time step size equal to that of time period, we will not able to see any vortex shedding. So higher the time steps, higher the accuracy of results. For current case, we have used two steps of 0.219 seconds and 0.145 seconds corresponding to 20 time steps and 40 time steps respectively. However, for this tutorial we will only show you the case where we have used time step of 0.291 seconds, but we will show you the results for both time steps. Here the concept of cycle, time period and time step is shown schematically. It is not necessary that the flow we are solving shows the exactly same pattern for vortex shedding, but it is just to give you an idea about the relationship between frequency and time period, and more importantly to give you an idea what does time step implies. So here we have divided one cycle into 14 equal parts. Please note this is just an example, but in our case we have used 20 times steps. Just for brevity of illustration, we have divided this into less segments. We call this time step or delta t. You can see if we divide this curve, between two peaks, into more segments, we will be able to produce the curvature more precisely. This is the basic logic behind selecting the time step for any unsteady CFD. We have selected incompressible and laminar formulation of RANs. Coupled, pressure-based solver is used for more accuracy and faster convergence. Second-order accurate schemes are used for all flow parameters. Second-order implicit option is used for resolving time effects for higher accuracy. Please try one case with first-order scheme to see the effects. Courant number is set to 2 million to speed up the convergence. Residuals are set to 1 to the power -15. Lift and drag monitors are used to record the drag and lift coefficients. Surface monitors are created to record the y velocity at the points shown in figure. For part 2 of this webinar we will only show you the surface monitor point 1, but we encourage you to create all 4 points and corresponding surface monitors. Please observe the transient behavior for monitors as well and their average, minimum and maximum values. We will use animation panel in calculation activities to make the animation for the vortex shedding. At the moment maybe you do not know how they are done in Fluent, but do not worry, we will show you all steps done in Fluent in part 2 of this webinar. The purpose of this presentation in part 1 of this webinar is to get you familiarized and give you general overview of approach we will be using while solving case in Fluent. In this slide, the panels for setting up drag, lift and surface monitors are shown. Now we will show you the results we have obtained from this simulation. We will also discuss results for different meshes and time steps. Please follow the part 2 at the end of this presentation for doing this case in Fluent. For steady-state cases, convergence is achieved when solution residuals are decreased by 3 to 4 order of magnitude and show the monotonic behavior. In addition to that, solution monitor such as for velocity or any other important parameter of interest attains the constant value and does not change from iteration to iteration. However, for transient simulation, solution is said to be converged, or more precisely periodically converging solution, when residuals and other monitors show the repetitive decrease and increase in magnitude for the number of iterations specified for that time step. However, it is to be noted that if residuals are not converging to specified convergence criteria, then you must lower the time step by at least half to the current time step. Which implies that now we will require double number of time steps to simulate the one vortex shedding cycle. Sometimes, CFD users try to solve the unsteady problems using steady-state approach without knowing it. However, it is very much easy to find out that your current approach is wrong by looking at the reseals and other monitors when they begin to show the cyclic increase and decrease in magnitude. Now it is the time to switch to unsteady CFD. In this figure, a surface monitor of y velocity at point 1 is shown as discussed earlier. Please note that when we will create this monitor in Fluent in part 2 of this workshop, you will notice that default name assigned to this point is point 6. Do not get confused, both are same points with different naming convention by us and Fluent respectively. You can notice initially y velocity is varying randomly, and after around 500 to 600 iterations, it has gained periodic pattern. Now solution is converged as per the unsteady CFD rules as we have just discussed. Now this is the time when we will start to collect the data for further processing, such as finding the average drag and lift coefficient, and we will show you the same shortly in part 2 of this workshop. Here we have a graph of y velocity at point 1 or point 6 as per Fluent naming convention. This graph is recorded for the last 2000 time steps. Please note that first 600 time steps are not included in this graph. From this figure we can conclude that the average velocity is negative 0.05 with maximum at 0.2 meter per second and minimum negative 0.3 meter per second. Second graph shows the instantaneous drag coefficient plots on cylinder, which also shows the unsteady behavior as expected due to periodic separation of flow on upper and lower surface of cylinder. From this graph, drag coefficient is approximately 3.13, as we will show in next slides and also in part 2 of workshop. For accurate calculation of mean drag coefficient, we will use Microsoft Excel and will import the instantaneous drag coefficient file and use some built-in to get the average drag coefficient. Here results for mean drag coefficient and Struhl number are shown for coarse and medium mesh for time step of 0.291. As you can see, the result for both meshes are in close agreement with each other and also to experimental data, which indicates the quality of our mesh, time step selection and other settings done in Fluent. For Struhl number we will use fast Fourier transform, commonly known as FFT. For more accuracy we should go for the large eddy simulation. In this slide results for time step 0.1453, which is half of the time step we have selected previously. This is just to see the effect of time step. It is recommended that you must select 3 time steps. Every next time step should be the half of the current time step. You should plot data for all time steps to confirm that results are not changing with changing the time step. This process is known as time-step sensitivity study, same grid independence study. It is observed that maximum difference between these two time steps is less than 2% in drag coefficient. And in Struhl number it is less than 4.7%. Please note that for both steps, data is collected for 2000 times steps. But it obvious that for lower time, we must have collected this data for 4000 time steps, which corresponds to equal vortex shedding cycles. Here vortex shedding is shown for some random time for coarse and fine mesh for time step of 0.145. Please watch the vortex shedding animation for fine mesh. Fine mesh case and data files are also available. To get these files, please send us an email. Here velocity pressure contours are shown for coarse mesh at time step of 0.145. It is again at some random time step. Here vector plot is shown for coarse mesh. Image on right hand side shows the close-up view of vector plot. For geometry generation in Design Modeler and mesh creation in Unsteady CFD Hexa, we will post the videos very soon. Please visit our page or Facebook to see these updates. If you are interested in some professional CFD courses or consultancy for your projects, please write us at given email address or leave us a message on our website. Thank you for your interest. Please watch the second part of video for doing settings up case and extracting results in Fluent in next part of webinar. After second part of webinar we will have 15 minutes question answer.